Hello dear students, how are you? I hope you are enjoying my online classes and also wish you happy Friendship Day. Keep the spirit of friendship alive. Moving ahead to our syllabus, in last couple of weeks we are revising chapter 12 and 13, that is current, electricity and magnetism, or magnetic effects of current, and that is your syllabus of term 1 also. From this week we will also be starting our class tests for your term 1, and let me give you a quick revision of chapter 12 and 13 in this video. So starting from chapter 12, the first topic is what is current. Current, represented by symbol I, is defined as rate of flow of charge. So charge divided by time, that is current. Unit of current is ampere, and 1 ampere of current is defined when 1 coulomb of charge flows in 1 second. The current is said to be 1 ampere. The second statement is Ohm's law. According to Ohm's law, V is directly proportional to I and V is equal to Ri, where R is known as resistance of the conductor and R is equal to V by I. The unit of resistance is ohm, and we can define 1 ohm if at the potential difference of 1 volt 1 ampere current is flowing. The resistance is said to be 1 ohm. We are having graph between V and I, that is always a straight line. If theta is the inclination of the graph, then we know that by the trigonometry, this is V perpendicular and this is I current. So tangent theta is also giving us the value of resistance. Okay, say theta is equal to 60 degree, then you can say that R is equal to tangent 60, and that is going to be √3 ohm. So you can solve the numericals like this. And if we are having graph of two conductors A and B such that angle of A is smaller than angle of B, then we can say resistance of B is greater than resistance of A. Fine. Next point is the resistivity, and for resistivity we are having relation R is equal to rho L over A, where L is the length of the conductor and A is the area of cross section and rho is the resistivity of this material. R is equal to rho L over A. Rho is known as resistivity. If I'll write the formula of rho, I can write it like RA divided by L. So rho resistivity is equal to resistance if your area is 1 meter square and your length is 1 meter. So resistivity is defined as resistance of a conductor whose area is 1 meter square and length is 1 meter. So that is your definition of rho, and we can solve several numericals using this formula. R is equal to rho L over A. Like for example, if length is doubled and area is halved, the resistance will become 4 times. Okay, and we have discussed the numericals already. After resistivity, in current electricity, the next point is about Joule's law of heating. According to Joule's law of heating, H is equal to I square RT, where R is the resistance of conductor, I is the current flowing, and T is the time. Using Ohm's law, V is equal to IR, I can rewrite this equation as H is equal to VIT or V square by RT. All these formulae are for Joule's law of heating effect. The fifth point is electrical power. Power is defined as energy or heat developed or dissipated divided by time. So if I divide my all these formulae with T, they will become formulae of power. P is equal to I square R, P is equal to VI, P is equal to V square by R. These are the formulae for power. And 6.1 kilowatt hour, that is our commercial unit of energy, is equal to 3.6 into 10 to the power 6 joule, energy consumed by 1 kilowatt device in 1 hour. And next we are having series and parallel combinations of resistances. We know that series and parallel combinations. So in series connection, resistances are connected like this. Head of one is connected to tail of other, and between points A and B, the equivalent resistance RAB will become R1 plus R2 plus R3, while this is your series connection. In parallel connection, resistances are like this: R1, R2 and R3. All the heads are connected and all the tails are connected. And for parallel resistances, we are having formula 1 by Rp is equal to 1 by R1 plus 1 by R2 plus 1 by R3, and so on if you are having more than 3 resistances. So these were the main points of chapter 12, that is current electricity. While in magnetic effects of current, starting from the Oersted experiment, which gives us relation that the current carrying conductor generates a magnetic field, we are having our first important topic, Oersted experiment, giving us relation between current and magnetic field. Then we are having our right hand rule for finding the direction of magnetic field in a given current carrying conductor. If we point our thumb in the direction of current, then curvature of fingers will give us the direction of magnetic field around the loop. Applying the same principle, we can also find the direction of magnetic field in a current carrying loop, and considering a loop made up of number of small conductors, the magnetic field will be like this. And by applying right hand thumb rule, direction will be inside in the interior and outside coming from the board in exterior of the coil. So this will become south pole, the clockwise direction, and the anti-clockwise direction will become north pole. So the magnetic effects of current chapter is mainly about the patterns of magnetic field. By applying our knowledge of magnetic field pattern, we can find that magnetic field pattern of solenoid. Suppose if the current is flowing from this and coming out from this, so this is your south pole, this is north, as clockwise and anti-clockwise you can see. So the magnetic field pattern of a solenoid is exactly similar to the magnetic field pattern of a bar magnet. In the interior of solenoid, magnetic field is pretty uniform, while in the exterior of the solenoid, magnetic field is strong near the edges, or poles. In the interior of the solenoid, field travels from south to north, but the exterior of the solenoid, this is north pole, the field is coming out, and this is south pole where field is coming in. So near the poles you can see the crowding of magnetic field lines, which is indicating stronger field, and where the lines are not that much crowded, like near middle section of the coil, so we are having weaker magnetic field. The bar magnet has similar magnetic field. Apart from it, we are having Fleming left hand rule, Fleming right hand rule, and electromagnetic induction, which we just have studied in previous lectures. Fleming left hand rule is applied when direction of magnetic field is given, say B, direction of current is given, say I. Then by Fleming left hand rule, first finger is pointing in the direction of field, second finger is pointing in the direction of current, then thumb will give you direction of force. So force will come out towards you in your direction. This rule we apply as application for DC motor when we are applying current and we are applying the magnetic field, while Fleming right hand rule is applied for finding the direction of induced current. Electromagnetic induction is the phenomena when magnetic field linked with a conductor changes, then an EMF generates in it, that is known as electromagnetic induction, and if we complete the circuit, then some current will flow, that is known as induced current, and the potential difference across the coil in which EMF is being induced is known as induced potential difference. So with these words I am going to finish this lecture. It was a quick revision lecture for you. Go through all the points, go through your NCERT book, solve few numericals. If you are having any doubt, you can ask me on Zoom classes, or I can have a video lecture like this for your problems. You can convey me on my personal number also. Like always, thanks for watching. Take very good care of yourself. Bye bye.